What if the key to unlocking powerful AI wasn't a new complex component, but simply taking one idea we already had and making it the only idea?
That's essentially the story of the transformer, an architecture that transformed machine learning by relying entirely on attention. The paper that started it all is famously titled "Attention is All You Need." This wasn't just a catchy name, it was a bold statement about a fundamental shift.
It really sets the tone, implying that this single mechanism could replace everything else in certain models.
Before the transformer, sequence models often used recurrent neural networks or convolutions. This paper proposed an architecture based solely on attention mechanisms, dispensing with recurrence and convolutions entirely.
Wait, entirely? I remember from hashtag TCM033005 that attention helps NRNs, but getting rid of the NRNs themselves seems like a huge leap.
That's precisely the central insight. Recurrent networks process tokens one after another, which inherently limits parallelization. But attention allows processing all parts simultaneously.
So if the transformer can process everything at once, it means it's more parallelizable and requiring significantly less time to train. That's a massive practical advantage.
The paper backed this bold claim with concrete results. It showed these new models were superior in quality while being more parallelizable. They achieved state-of-the-art on tough machine translation tasks.
So not just faster, but better too. That's the dream, isn't it? Better results with less computational cost?
The sequence transduction problem means transforming one sequence into another, like translating English to German. Historically, dominant sequence transduction models are based on complex recurrent or convolutional neural networks.
So the transformer was designed to tackle this specific problem, but with a radically different approach. It replaces complex architectures with just attention.
They didn't just tweak an existing system. They state directly, we propose a new, simple network architecture, the transformer. Simplicity here is deceptive. It's a profound shift in thinking.
Simple in architecture maybe, but the underlying idea feels quite deep. This foundational model reshaped the entire field.
In TCM-033005 and TCM-093003, we explored how attention allows models to weigh the importance of different input parts. The transformer took that concept and asked, what if that's all you needed?
It's like they distilled the most effective part of previous models and built a whole new one around it. The transformer truly generalizes this idea.
To truly understand how this attention-only approach works, we need to peel back the layers and see how the transformer encodes information.
So how does it build meaning without sequential processing? Let's dive into the core components.
Let's start with a high-level view, treating the model as a single black box. If we feed it a sentence in one language, it outputs the translation in another. Simple on the outside.
Like a magic translator. But we know there's a lot more going on inside, especially given its all attention.
Popping that box open reveals two main parts, an encoding component, a decoding component, and connections between them. This encoder-decoder structure is common in sequence transduction.
So the encoder processes the input sentence, and the decoder generates the output sentence using the encoder's work.
Each component isn't just one unit. It's a stack of encoders and a corresponding stack of decoders. The original paper used 6 of each, but the number is a hyperparameter.
It's a modular design then. Each encoder refines the representation before passing it to the next, similar to layers in other deep networks.
Inside each encoder, the encoder's inputs first flow through a self-attention layer. This is where the mechanism for understanding context operates, especially for each word.
So self-attention allows a word to look at all other words in the input sentence. How does that help resolve ambiguities like it in a sentence?
The illustrated transformer gives a great example. What does it in this sentence refer to? Is it referring to the street or to the animal? Humans understand this from context, but for a machine, it's tricky.
This is a classic NLP problem. In an RNN, the hidden state would build context. But how does self-attention manage that without sequential memory?
As the model processes it, self-attention allows it to associate it with animal. It effectively learns how important other words are to understanding the current word.
So when it is processed, self-attention gives a high score to animal, essentially blending animal's meaning into its representation.
We can think of how maintaining a hidden state allows an RNN to incorporate its representation of previous words. That's a sequential process. Self-attention achieves a similar goal, but in parallel.
So the analogy of contextual understanding is exact, but the mechanism is radically different. Parallel attention versus sequential hidden states. That's a crucial distinction.
Another key property is that the word in each position flows through its own path in the encoder. While there are dependencies between these paths in the self-attention layer, the feed-forward layers are independent.
That explains the parallelization. Each word's path can be computed independently in many parts, except for the attention step that creates the dependencies.
To understand how self-attention achieves this contextual blending, we need to introduce three fundamental vectors derived from each word: query, key, and value. These terms sound like database lookups. How do they work together to create this associative memory for words? The first step in self-attention is to create three vectors from each of the encoder's input vectors for each word. These are called the query, key, and value vectors.
So every word, after being embedded, gets transformed into three distinct representations. How are these Q, K, and V vectors generated?
They are created by multiplying the embedding by three matrices that we trained during the training process. These learned matrices project the word embedding into different conceptual spaces.
So the model learns what to ask for, query, what to look for, key, and what information to provide for each word. This is not hard-coded.
Think of it like this. Your query is what you're searching for in a library, like novels by Jane Austen. The key is what identifies a book, like its title, Pride and Prejudice. The value is the actual content of the book. While this helps illustrate how query and key match and value hold content, it's important to remember that in self-attention, for a single word's query, we get a blended representation from all other words' values, not a direct retrieval of individual items like from a library shelf. Next is scoring. For each word, we calculate how relevant every other word is. The score is calculated by taking the dot product of the query vector with the key vector of the respective word.
So if I'm processing it, its query vector is dot producted with the key vector of animal and street and every other word. Higher dot product means higher relevance.
After dividing by the square root of the key vector's dimension, dk, a crucial step for stabilizing gradients and preventing the dot products from becoming too large, we pass the result through a softmax operation. Softmax normalizes the scores so they're all positive and add up to 1. These become our attention weights.
This makes sense. The softmax turns the raw scores into a probability distribution.
showing how much attention each word should get for the current word.
Finally, we multiply each value vector by the softmax score and sum them up. This forms the output of the self-attention layer for that specific word, a new contextualized representation.
So the output is a weighted sum of all the value vectors, where the weights are determined by how relevant each key was to the current query.
We talked in hashtag TCM00330005 about attention being a learned interpolation rather than just a lookup. Here, the query key interaction determines the interpolation weights, and the value vectors are what get blended.
So the attention mechanism is essentially deciding what information to pull from other parts of the sequence and how much to weigh it when constructing the representation of the current token. It's truly dynamic.
This parallel processing is a huge win, but does it come with any downsides? For example, with attention is all you need, if we double the length of our input sentence, how does the computational cost change?
That's a critical point, Maya, because each word's query has to be compared with every other word's key. The computation for self-attention grows quadratically with the sequence length. This O of n squared complexity means transformers can become very expensive for extremely long texts, which is a known limitation that researchers are actively working to optimize with more efficient attention mechanisms. One subtle but important aspect of attention is that by itself, it's permutation invariant. This means dog bites man and man bites dog would produce the same attention scores because the mechanism just sees a set of words.
So how does the transformer account for word order, which is crucial for meaning, if attention doesn't care about it?
That's where positional encoding comes in. Before tokens enter the transformer, we add a numerical signal to their embeddings that encodes their position in the sequence, giving the model crucial information about order without sacrificing parallelization. Exactly. After embedding the words in our input sequence, but before passing them to the first encoder layer, the transformer adds positional encodings. These are mathematical functions that generate a unique vector for each position in the sequence.
So each word's embedding gets tagged with its position. This allows the model to differentiate between dog bites man and man bites dog, even though the self-attention mechanism itself is order agnostic.
Precisely. The model then learns to interpret these positional signals alongside the word's meaning. It's a clever way to reintroduce sequence order information without forcing a sequential computation. What we've described so far is a single attention head. But the transformer doesn't just use one, it uses multi-head attention.
Multi-head? So instead of one set of QKV matrices, there are multiple? Why?
Yes, the transformer was proposed in the paper Attention is All You Need with 8 parallel attention heads. Each head performs the query key value attention mechanism independently with its own learned set of Q, K, and V weight matrices.
So for every word, we're not just getting one contextualized representation, but 8 different ones, each potentially focusing on different aspects or relationships within the input sequence.
Exactly. After each head calculates its own output, these 8 different context vectors are concatenated or joined side by side. This forms a much larger vector.
And then what? Do all these separate pieces of information get combined into a single unified representation again?
Precisely. This large concatenated vector then passes through a final linear layer, another learned weight matrix, that transforms it down to the desired output dimension, effectively combining the insights from all the attention heads into a single, richer representation. The benefit is similar to having multiple experts look at the same problem from different angles. One head might focus on grammatical dependencies, another on semantic relationships, and yet another on negations. Combining their insights leads to a more robust and comprehensive understanding of the input.
So, multi-head attention allows the transformer to capture a wider range of relationships and nuances within the data simultaneously, contributing to its power and efficiency, which is why it is in fact Google Cloud's recommendation to use the transformer as a reference model to use their cloud TPU offering.
After the multi-head attention mechanism has created a rich contextual representation, the outputs of the self-attention layer are fed to a feed-forward neural network.
Is this a standard neural network layer, like the ones we've seen before?
Yes, it's a simple two-layer fully connected feed-forward network, but it's applied independently and identically to each position in the sequence. It acts on the output of the attention sublayer to introduce nonlinearity and allow the model to learn more complex, position-wise transformations of the contextualized representations. Think of it as further processing the meaning of each word in isolation after its context has been established by attention, increasing the model's overall representational capacity.